A question for you all. What is the difference between a discrete random variable and a continuous random variable? Yes?
Discrete is like a whole number and continuous is like...
Right. A discrete has a finite set of outcomes. We think of them like whole numbers, although we could think of like 1.1, 1.2, 1. There's got to be a gap between things, right? And that's why we went with a histogram. We could do frequency. How many times did this number come up? How many times did this number come up? And a continuous random variable has a range. There's no gap necessarily required between options. If I turn around and I ask you, how tall are you? I'm 5'10". Well, then I go and I get on the scale at the doctor's office. They measure me. Not quite 5'10". I'm really a little bit bigger. How far do you want to go down the scale of being accurate, right? Because with a measurement like that, I can measure to any precision I want. That's what we define as a continuous behavior. And it's not realistic to think of the probability of getting an exact value. My driver's license says I'm 5'10". My records at the doctor's office say I'm 5'10", but I'm not really exactly 5'10". I'm a little bit over, but just a little. And so thinking about will you be exactly this particular number is very hard with a continuous random variable. So rather than try and nail down the idea of being exactly equal to a number, most of the time when we deal with continuous random variables, we're going to deal with ranges. What's the chance the number I get is between 5'10" and 5'11" when I start measuring people's heights? Or what's the chance that I get a weight between 180 and 190? When we were doing discrete random variables, we had a column. We had a frequency histogram, and we said we're looking at the things in this column, or we're looking at the things in a couple of columns. But now that we're looking at a range, I have to figure out a slightly different way to describe my probability density function. So the new question now is, what's a PDF and a CDF look like in this case? And here I'm about to say some terribly scary words, and I promise you shouldn't be terrified, because that's about all we're going to do about them is say the words. In a histogram, we looked at the bars, and we said, this bar has a size of 1/8, this has a bar of 3/8. We add them together, we get a 4/8 chance of something happening. But now I don't have a bar, I have a range, which means instead of looking at distinct separate objects, I'm looking at a continuous graph. So really, a PDF is the graph of a function. Algebra class, I got to go all the way back to algebra class and think about graphs of functions. I have the x-axis, I have the y-axis, I have a piece of graph paper in my head at the moment, and I draw some sort of a shape, and that shape is the graph of a function. If I want to be more pedantic, I need to go back and think about my probability rules. We know that any event has some probability, right? So if I go and I look at this event, I should get some number. What do you know about the number that is the probability for this event? The same thing you know about the numbers that came out of a probability in chapter 5. Probability of a thing is some number. What do we know about that number? Came up with 2 rules about probabilities way back at the beginning of chapter 5. Find them for me. Before we did all these crazy Venn diagrams, and you way back at the beginning, probability of an event. Does that help? Aha. Every probability must be a number between 0 and 1. Well, if that's true, then this result must be between 0 and 1, which means my function has to be between 0 and 1. I can never get any negative numbers out of my function, which means the graph never goes down here. It's always above the x-axis. What was the other rule for that pile? It's literally the next line in your notes after this. Find this in your notes. It's the very next line. The total of all of my probabilities has to be equal to 1. Now, here's the problem. I no longer have the ability to look at bars on a histogram because I have this graph instead. Maybe it's something that looks like that normal distribution bell curve shape. Maybe it's something else because our graph can look like different things for different PDFs. Something like waiting in line. You go downstairs to the caf, you get in the line for lunch, you're going to go through the main line. How long is the line? How long is it going to be till you have food on your plate? It could be 30 seconds. It could be 8 minutes, right? But the chance of it being a long time is probably pretty small, isn't it? The chance of being a short time is probably pretty quick, probably pretty high. So what I could say is maybe that my PDF graph looks like this. Now, please notice, it doesn't make any sense to have x be negative. You can't wait negative 1 minute in a line, right? You got your food before you got in the line. Poof, magic, time travel. And the chance that you wait a very short time is pretty high. The chance you wait a long time is pretty small. My issue here is that this is a continuous thing, not a discrete thing. So the chance you wait exactly 2 minutes is really very hard to find. But I could ask, what's the chance you wait between 1 minute and 2 minutes, couldn't I? And if that's the case, 1 minute is a mark down here, and 2 minutes is a mark down here. And the chance you wait between 1 minute and 2 minutes should be that bar, right? I don't know how to find that bar, because technically that's not a rectangle. It's got that funny curvy slopey top there. Here's the scary word. What I really want is the area under this curve. Find areas under curves, you use calculus. We will never, ever do calculus in this room. But somebody's done it all for me, so I have that information in front of me. But if the total of all of my probabilities is 1, then the area under this curve, the total area, should be 1. And that is the key piece of this entire chapter. What we were doing with computational formulas and looking at the different bars of my histogram and adding up the number of options is now done about finding areas under curves. And that means technically I should be doing calculus for this. We're not going to. But our ideas from discrete probability still carry over. Each PDF will be somehow described by a function, and we'll be able to look at its mean and its standard deviation. And we can do all of that in calculus terms. Not going to happen here. So let's consider whether or not a particular function is a PDF or not. So didn't write down the page number. That was done with me. On page 235, here is a couple of functions. Question 3, page 235. Here I have a function whose output is 1/4, 0.25. For 0 less than or equal to x less than or equal to 1. And that same function is 0 everywhere else. So if I were to graph this function, what would it look like? This is where I need you to dig back into your algebra skills. Y equals 1/4. I'm sorry, what's that? It'd be a straight line, right? It'd be a horizontal line. But it would only be that horizontal line between 0 and 1. Everywhere else, my graph is 0. So here's my question for you. Is this a PDF? Probabilities have to be between 0 and 1. All of the outputs are between 0 and 1, aren't they? In height. The y values are between 0 and 1. So I'm good with that part. What's total area under this curve? It's a box. What's the area of a box? Length times width. It's 1 unit long. It's 1/4 unit high. The area under that is only 1/4. Oh, wait a minute. Length times width, 1 unit long, 0.25 high. That's 0.25. That's not 1. Not a PDF. Here's a different function. What's the graph of that one look like? So it's basically the same picture, it's just stretched out further, right? And again, I say the same thing. Is this a PDF? I'm getting some no's and I'm getting some yeses. Wait a minute. Tia, tell me why no. What should be equal to 1? The total of all of the probabilities should be equal to 1, and that's the area under this curve. So what's the area inside this box? Same calculation we did up here. The area in here, length times width, is 4 times 0.25, and that is 1. Now, you're right to ask, are all the y values in the right place? And in this case, all the y values have to be between 0 and 1. No y value has to actually be equal to 1. Think about our coin flip idea, right? We had a probability of 1/8 of getting no heads, 3/8 of getting 1 head, 3/8 of getting 2 heads, and 1/8 of getting 3 heads. None of the probabilities were equal to 1, but when I added them all up, I got a 1. And all of the y values here are between 0 and 1, even if none of them actually ever is 1. Remember, if my probability of something is 1, then that thing must happen. Always. The only event I can guarantee you that must always happen is the things that you go up must come down eventually. So, one more. Here, our function is defined to be f of x equals x from 0 to 2. Yes, sir. Yeah, well, I got to draw a picture first. What's the picture look like? Aha. So this line goes this way instead of being horizontal. And that's why I mentioned specifically horizontal, because all lines are straight. That's the definition of a line. But this line is at an angle, and it stops at 2. And since y is equal to x, that means that when it stops, it's at a height of 2 as well. The x value is 2, the y value is 2. What's the area under this curve? Triangle, right? The area for triangle is 1/2 base times height. Base of this is 2. The height of this is 2. Wait a minute. Nope. That area is 2. How else could I have known this was not going to be a PDF? I needed my y values to stay smaller than 1, or at least I needed the areas to stay smaller than 1, right? So the fact that that goes up to 2 makes me kind of weirded out. Yes, but those are very, very complicated looking things, because if I want the total area under my curve to be PDF and part of it is above 1, then there better be an awful lot of very low stuff somewhere else, right? Those are weird looking. And a guy by the name of Dirichlet in the late 17 and 1800s, late 1700s, early 1800s, was working on that sort of idea in physics. So there are places where that works, but it's not going to happen around us. For those of you that have seen a calculus course, the area under a curve is an integral. That elongated squiggle there, that's a capital, elongated S. And it's like our sigma. Hey, wait a minute. Like our sigma for sum, that's what that means. You add up all the area under your curve. Long squiggle from A to B, f of x, dx. Dx means that I'm looking at my rectangles along the x-axis. We had 2 formulas, a formula for average and a formula for standard deviation. And the formula for average took all of my probabilities and multiplied them by x, didn't it? It multiplied each one by its value. Well, if I stick an extra x in there, that's how I get a mean. And in our standard deviation, well, it was really our variance. In our variance, we took x minus the average, and then we squared it and multiplied by the things. So there are calculus ways to do all of the things we are going to do. If you don't even bother to write these formulas down, that's fine. You will never have to do the calculus part of this in this course. Yes.
Is there like a term for the elongated S?
It's called the integral symbol.
Okay, thank you.
Yes. Technically, the integral elongated S is developed by Riemann in the mid-1800s. It really gets its full usage from a bunch of other math geeks, Laplace, Euler, and a bunch of those other famous math geek guys. But yeah, that integral symbol, because that's what we're doing with integrals in integral calculus. This is the second half of Calc 1, like from February on for the AP Calculus class. You're welcome. I want to address, please notice I did not put A's and B's on these 2 integrals, because technically I want the area under the whole curve, right? And that means I might have places where my x value could be negative. I might have places where my x value could be positive. So technically, these should be integrals from minus infinity to infinity. And that is a major, major unpleasantness. Again, you won't actually ever do the calculus part here. More questions? I want to try and focus on the same sorts of things we were doing in the last chapter. I only did 2 distributions last chapter, right? I did the uniform distribution and I did the binomial distribution. The uniform distribution, everything had the same chance of happening, right? Isn't that what this picture looked like right here? Every event has the same probability. That was our uniform distribution. So I can define a uniform distribution continuously. And it's going to look just like the picture we were just looking at. My graph is going to be a horizontal line. Now, I want the area to be 1, right? I want the total area to be 1. So let's suppose we went from A to B. I want the area inside this rectangle to be 1. First question, how long is the rectangle? From left to right. How would you figure out that distance? Say again? If I added, then I would go past the end of B, wouldn't I? Say again. It'd be B minus A. Okay, wait a minute. So the length is B minus A. I want the area to be 1, and area is length times width. Since the area is 1, that means I know what the width is. The width should be 1 over B minus A, and that's the y value right here. Yeah, that's why when I went from 0 to 4, I got a height of 1/4, because those match exactly up to give me an area of 1. But this means I can do this between any 2 numbers. I could do the area from 7 to 26. I can do the area from -5 to 5. We're going to write this function as u a comma b of x. The absolute best thing about this distribution is that the mean and the standard deviation are exactly the same as they were for the discrete version, which means that the mean, or the expected value is exactly in the middle, halfway between A and B. Now, the standard deviation calculation is a little bit more of a pain in the neck. I did tell you we didn't know how to do it last time, but if I can do the calculus, I'll save it for the calc class. It turns out that the standard deviation, the square root of B minus A squared over 12. Let me suppose that I had some sort of experiment where I expected this sort of a probability. In terms of surveys and such, you have to use this sort of a model if you expect, hey, no one's likely to give any one answer over another. My measurement is not likely to provide more of one answer over another. This is a useful assumption, but if you had any sort of trends in your group, if I'm measuring height or weight or something like that, it depends on where I am. If I measure height outside 131 down at the bottom of the hill, who's more likely to go in and out of the building at 131? Anybody know what team practices down in 131? Wrestling team practices down there. Most wrestlers that I know are short, not tall. They're broad, but they're shorter. On the other hand, if I go down to McKenna and I ask people their heights, well, the basketball court is right there, isn't it? I'm more likely to get basketball players. I'm going to skew my data. I have a convenience survey bias. Remember back from chapter 2? So I would lose those sort of nuances if I assumed this about a model. That's not to say these aren't inappropriate models. They're just going to require that we make different assumptions. There is an Excel formula for this distribution on page 236. But because of the way this distribution is drawn, I rarely, if ever, use this formula in Excel, simply because I think it's easier to actually draw the picture and figure out areas. I'm going to tweak the question a little. One of the questions in the textbook talks about the arrival time of a bus. And the bus is scheduled to arrive at 10:20. But it's a bus driver. Bus drivers are rarely perfectly on time, yes? And it turns out that we actually can say that the bus's arrival is better modeled by a uniform distribution. We're not more likely to have the bus show up later than earlier, but most of the time, the bus arrives between 10:18 and 10:23. On average. When's the bus get here? The formula for this just scrolled right off the top of the screen, so you should already have it written down. What's the average? The length that gives me the whole window. So from 1018 to 1023 is the whole window. Where is the average on that window? It's right in the middle at 1020.5. We should take the 2 times and add them together and divide by 2. And yes, that is 1020.5. Which means, on average, the bus is 30 seconds late. What is the probability that the bus is earlier than scheduled? That would be earlier than average, right? But it's scheduled for 10:20. So really what I'm asking is what's the chance that my arrival time is between 10:18 and 10:20? Now this is where you might think, oh, well, I need some formula for this. That's my graph, right? It's a horizontal line between 1018 and 1023. What's the height? One-fifth, right? 5-minute window. The area has to be 1, so the height is 0.2 or 1/5. But now I'm asking you, what's the chance it's between 1018 and 1020? How wide is that window? That's only 2 minutes, right? So the area inside this box is 2 times 1/5 or 0.4. The chance is 40%.
Is that including 1020?
Yes, it's up to and equals, right? Why? Because that's a really legitimate question. Remember, we said it would be very hard to figure out what is the chance that the bus arrives exactly at 10:20. Because then I would be asking for the area starting here and ending here. How much area is under that piece of the graph? That's there's no area between those, right? Because the width of that window is 0. So this, if I include this edge, that would be just this little bit. That's got an area of 0. And it doesn't make sense to add up a bunch of zeros. So whether you use 1020 or you say, no, I just want to go less than 1020, actually makes no difference in this case. The chance is still 40%. Because that one little sliver of an end doesn't contribute anything to my area. Believe it or not, that's one of the fundamental questions of calculus. Is there's nothing there. How can you add up a bunch of little nothings? So if you're interested in that, there's a really nice history of mathematics course next semester in your copious free times, right? There are several very good books on the history of calculus, but that actually got a lot of math people in trouble with the church. Lovely discussion on that after class. But you're right. Whether I include the end number or not doesn't actually make a difference. Because how close to 1020 am I going to get? 10, 15, 10, 19.59999999. I'm at 1020, aren't I? At least according to my watch, which only has 1-digit seconds.
But you would just say less than 40%.
No, I'd say it's exactly still 40%. That's the funny part. That one little thin layer on the end has no area in it. If I took away that one little bit, I took away a zero. 40% minus zero is still 40%. This is what's weird about calculus, man. It really is a crazy idea. And as a matter of fact, if you look at question 7 here you go. Question 7 right here. For a continuous distribution, 25 less than x less than 45 is the same as 25 less than or equal to x less than or equal to 45. And the answer to that is because that's the way calculus works. And that's messed up. Because I don't know how to do exactly one number. I have to use a range. Whether or not I use the edge of that range doesn't add or subtract any area under my curve. No matter how thick the line on my pencil is, mathematically, it's infinitely thin. Technically, there's no area in there, but I can't draw that. If the chance my bus arrives early is 40%, the chance my bus arrives late is 60%. What's the chance it's running really late? What is the chance that my x value is bigger than 1022? Hey, wait a minute. You didn't put another number on the other side. Our numbers only go up to 1023, so this is the same as saying go to 1023. What's this chance? Draw me a box. It would be 20% because my box goes from 1022 to 1023. And that width is 1 minute. 1 minute times a height of 0.2 gives me 0.2. Questions? Realistically, I have never done any sort of calculation for a uniform distribution that wasn't really find the area of a box. Maybe it's find the area of more than one box and add them together. But that's about it. Once my distributions get more complicated, things get harder. Talk to me.
Where did we get the 1/5?
It's because we have 5 minutes in our window, and our height is 1 over the length. Our length is 5, so it's 1 over 5. It's absolutely an important question. Don't let blow by you, people. Slow me down. Because we're finally getting the stuff that I like about this, and that's going to piss some of you off because I'm moving faster. No, don't do that. Trip me up. Ask me the questions. That normal distribution curve we looked at earlier is a PDF. That's our bell curve. It's also called the Gaussian distribution. Carl Friedrich Gauss studied a lot of the properties. Now, we need two different pieces of information because a normal distribution is defined by its mean and its standard deviation. So I need two parameters. Once I have those, I can write the equation for the function that gives me that bell-shaped curve. The equation for that function is absolutely mind-blowingly, gut-wrenchingly ugly. I'll write it down. You don't have to. That is the nastiest looking mother I've seen all day. Don't bother. What this tells me is that my curve will have its center at the average and it will spread out from there based on the size of my standard deviation. If my standard deviation is large, we'll get a very wide, shallow curve. If my standard deviation is small, we'll get a very tight looking curve with a very sharp peak in the middle. But every single normal distribution really can be thought of as living between 3 standard deviations down and 3 standard deviations up. Wait a minute. We had this rule for normal distributions with some percentages, didn't we? Back in chapter 4, we had that empirical rule that said that if here's my average, there's my mean, my bell curve looks something like this. If we have 1 standard deviation up or down, that's 68%. If we went 2 standard deviations up or 2 standard deviations down, that was 95%. And if we went 3 standard deviations up or 3 standard deviations down, that was 99.7%. So that means way up here, above the 3rd standard deviation, there's a really, really, really tiny amount of area. Page 238, figure 7.7. There's our PDF. And next to it, there's our CDF. The CDF does not have a formula I know how to write down. It's disgusting. There isn't a nice formula for you. So how do I find areas under this thing? I'm not doing calculus. We'll talk about that on Monday. Please note, your homework is due on Monday. If you have questions, you should be emailing me over the weekend. If you came in late and I still have your homework, please come get it from me. That's how I'm taking attendance today. See you all on Monday.